Thank you for staying on a Friday afternoon. And my name is Chris Lee. I'm a groundwater modeler from Juna. And today I'm going to talk to you about how we can help the River Murray floodplains. More specifically, how we can improve the soil and vegetation conditions there. And before I begin, I would like to share with you a field trip that my team had to the Riverland. We went to many different places, and one of them was the Pike floodplain. Here's a photo I took there. You can see there's a white patch. What is this white patch? This is salt. There is a lot of salt on the floodplain, and too much salt is harmful for the trees. In the second photo here, you can see the trees are having very poor health. They are suffering, they are dying. So let's save the trees. Let's save the floodplain. But how do we do it? Our department and the MDBA have initiated a 7-year joint project called SAFIP. It stands for South Australian Riverland Floodplain Integrated Infrastructure Program. And let's begin with a conceptual diagram. So there are a few trees suffering at the ground surface. And at a certain depth, there is the saturated zone. It is filled with groundwater, and the groundwater contains a lot of salt. And between the ground surface and the saturated zone, there is the unsaturated zone. This is the focus of this study. And because of evaporation concentrating the salt, the unsaturated zone contains a lot of salt. And too much salt is bad for the trees, and we would like to remove or reduce the amount of salt from the unsaturated zone. So how do we do it? Under SAFIP, there are 2 proposed management options. The first one is managed inundation. So this is about let's flood the floodplain and flush the salt down to the saturated zone. So this is the first option, managed inundation. The second option is groundwater manipulation. So let's say we have a freshwater lands next to a river, and if we pump the groundwater out, this will lower the groundwater level, and this will induce leakages from the river, extending the freshwater lands. And this may have a positive impact on the overlying soil salinity. So this is the first benefit of groundwater manipulation. It also has an additional benefit of lowering the groundwater level. So this can reduce the amount of saline groundwater going up to the unsaturated zone. It can also offset the water table rise due to inundation recharge. But the focus of this study is on the impact of extending the freshwater lands. So now we have got 2 options. We have got managed inundation, we have got groundwater manipulation. And the questions are they effective? And how effective are they? To answer these questions, well, let's do some modeling. So we have developed a series of 1D hypothetical model using lithium. Lithium is a numerical code that is capable of simulating fluxes of water and solid in the unsaturated zone. And our models consist of 2 meters of the conambitual clay, followed by 1 meter of the monument sand, and underneath is the saturated zone filled with saline groundwater. And we acknowledge that the floodplain environment is spatially highly variable. Therefore, during the modeling, we have considered different possibilities. For example, there may be cracks in the clay. There can be different vegetation types on the floodplain, and they have different root depths. And depending on the area, the groundwater can be shallower in some area, can be deeper in other areas. Therefore, we have also considered different groundwater depths. And we have considered 4 management options. The first one is, what if we do nothing, business as usual? The second one is groundwater manipulation. Third one is managed inundation. And the fourth one is a combination of both. So combining all these possibilities results in 80 scenarios. And because of time, I won't show you the results for all the 80 scenarios. I will focus on the base case, which assumes there's no crack in the clay, and a root depth of 1.5 meter, and a groundwater depth of 3 meter. So there are many things that lithium can tell us. For example, it can tell us how each water balance component changes over time, the amount of water fluxes across the model layers, the salt mass profile, and the soil pore water salinity for each of the model layers. But again, because of time, let's throw all this away, and let's just focus on 2 things. The cumulative drainage and the average soil pore water salinity. If we look at the block diagram here, drainage is the flux across the bottom of the unsaturated zone. And the salinity you see in the bottom graph is the average for the entire unsaturated zone, including the clay and sand layers. And the blue line you see in the graphs are the results for the no action scenario. So what they are showing is that the top graph, it is showing that there is minimum drainage to the saturated zone. In other words, there's minimum flushing. And the bottom graph, it shows that if we do nothing, then the unsaturated zone will remain highly saline. So this is what it looks like conceptually. So if we do nothing, then the unsaturated zone will continue to contain a lot of salt. So what about groundwater manipulation? Let's look at the red line in the graphs. So in terms of drainage, similar to the previous scenario, there is hardly any drainage to the saturated zone. There's very minimum flushing. But if we look at the salinity graph, what we find is that there is some degree of freshening to the soil profile. That is nice. So let's look at the conceptual diagram. What we find is that extending the freshwater length can have some positive impact on the bottom part of the unsaturated zone. However, it does not have much impact on the overlying soil salinity. And what about managed inundation? In the scenario models, each inundation is 100 days long and occurs once every 3 years. And, and let's look at the green line. So in the drainage graph, you can see there's a lot of drainage to the saturated zone. There's a lot of flushing. And if we look at the salinity graph, you can see there's a significant reduction in soil salinity. So that is awesome. And I probably should mention that this is an optimistic case. So we assume the clay is relatively permeable. And if we look at the green line in the salinity graph again, you will notice there are spikes. You may wonder what are causing these spikes. Let's look at the conceptual diagram. So what we find is that managed inundation is capable of flushing a lot of salt down to the saturated zone. And then the trees are happy now. And because they are happy, they drink like crazy. And therefore, there is a likelihood for the saline groundwater to be drawn up, and therefore causing those spikes that we saw in the last graph. And what about a combination of both? Let's look at the purple line. So similar to the previous scenario, there's a lot of drainage to the saturated zone, there's a lot of flushing. And if we look at the salinity graph, you can see that, yes, there's also a significant reduction in soil salinity. And in addition, this time it doesn't show those spikes as the green line shows. And this is because this time the water in the saturated zone is fresh. And therefore, even if it goes up, it won't bring too much salt to the unsaturated zone. Therefore, it doesn't have any spikes. And again, this is an optimistic case where we assume the clay is relatively permeable. So this is what it looks like conceptually. All the salt going down and not coming back. And then the trees are happy. Good ending, huh? But is this the end of the story? No, not yet. There's a big however. What is this about? So if we look at the managed inundation scenario again, what we find is that the effectiveness of inundation is highly dependent on a few things. For example, it depends on the root depth. So if the roots are deep, when the tree takes up water, it is more likely for the saline groundwater to be drawn up. And similarly, it also depends on the groundwater depth. If the saline groundwater is shallow, it is more likely to be drawn up to the unsaturated zone. And what we find is that the most critical variable is the clay permeability. Let's have a closer look at this. So previously, we were looking at results, we were looking at the optimistic case. So this time, let's look at the not so optimistic case. So what if the clay is less permeable? And we test this by dividing the clay permeability by 10. This is the lower end of the expected realistic range. And let's look at the black line. In the drainage graph, it shows that there's hardly any drainage. There's hardly any flushing. And if we look at the soil salinity graph, you can see that if we look at the black line, there's no sign of freshening at all. And if we look at the conceptual diagram, what we find is that if the clay is less permeable, then the inundation may infiltrate very slowly. And after the inundation is gone, then evaporation just takes away the water. And therefore, there's hardly any flushing of the salts down. And the floodplain environment is spatially highly variable. For example, in some areas, the clay may be more permeable. In some other areas, the clay may be less permeable. And therefore, different parts of the floodplain are going to respond to the management actions differently. And we shouldn't expect uniform recovery from the management actions. So in conclusion, for groundwater manipulation, the extended freshwater lens has some freshening impact on the bottom part of the unsaturated zone. And it also has the benefit of lowering the water table, which can offset the water table rise due to inundation recharge, but that is not the focus of this study. And for managed inundation, yes, it has the potential to reduce the soil salinity under some conditions, and its impact is highly dependent on the clay permeability, the vegetation root depth, and the groundwater depth. And using a combination of groundwater manipulation and managed inundation appear to be the optimum solution. And this work has formed the basis for further work that can inform the expectations of floodplain responses to the management actions and also inform the monitoring and evaluation planning. Thank you.